right, welcome everybody. So today I want to talk about one of the newer projects going on in OpenJDK. At the keynote this morning, I showed a long list of projects: Loom, Panama, Valhalla, Babylon, and Leyden is one of the newer projects we started working on it maybe 6 months ago or so, which is aimed at improving startup and warm-up of Java applications. So to define our terms a little bit. What is startup and what is warm up? Startup is the amount of time it takes to get to the first useful unit of work. Warm up is the time it takes for an application to reach peak performance. So both of these things include a mix of activities, both work that is done by an application and work that is done on behalf of an application. So if you have a typical server application, when it starts up, it's going to go through the usual: parse the configuration file, open some sockets, create listeners, create loggers, create more loggers, create a lot of loggers. And that is work that is done by the application. At the same time, the JVM is doing work on behalf of the application. It's loading classes, it's validating class files, it's JITting classes, it's resolving constant pool entries, it's symbolically linking call sites, things like that. And startup and warm-up are an issue for some Java applications, not for all. But the reason I want to talk first a little bit about where these issues come from, if they are issues, and then what we're doing to offer a range of choices to make it better. The main reason why startup and warm-up are an issue for Java applications is because of Java's dynamism. And some of you are thinking, probably, wait a second, I thought Java was a static language. So I want to talk about the terms static and dynamic because they're frequently misused and abused. And they mean a lot of different things in different contexts. So I'm going to start with a very simplistic notion of static versus dynamic, which is wrong, but we'll get to something better, where let's assume that static means at compile time and dynamic means at runtime. Like I said, not a good starting assumption, but we have to start somewhere. So the question I would ask is Java statically typed or dynamically typed? The answer is on the slide, so it's not really a question. The answer is yes. The answer is Java is both statically typed and dynamically typed. So Java has a static type system that's enforced by the compiler. And it has various rules about conversion and overload selection and such. Java also has a dynamic type system, which is enforced at runtime by the JVM. And the two have a lot in common. In both the static and dynamic type systems, string is a subtype of object, but they also have significant differences. And it's not that one is a pure subset of the other, although in general, the dynamic type system tends to be weaker than the static type system. And that's true across a lot of languages. But for example, some things that are part of the static type system that are not part of the dynamic type system are things like generics. We type check generics at compile time, and then we erase them away. The checkedness of exceptions also happens to be something erased away at compilation time. Not everybody's aware of that. Definite assignment analysis is part of the static type system. So in Java requires that you initialize a local variable before you use it. The JVM doesn't enforce that, but the compiler does. Overload resolution is another of these what we call language fictions, which is checked at compile time and then ignored thereafter. On the other hand, there are aspects of the dynamic type system that are not part of the static type system. The best example of that is array store exception. So if I have an array that is an object array, and I go to store a string in it using the AA store bytecode, I may get an array store exception. And the reason is that object array might actually be an array of integers. It may be an integer array because arrays are covariant in Java. So I can cast an integer array to an object array. And then if I try to put a string into it, the runtime will say, no, you can't do that. So this is all a long-winded way of saying that even the simplistic notion of static and dynamic are about compile time versus runtime, and that static and dynamic are only about typing, even with these simplistic assumptions, Java doesn't fit neatly into a category of static or dynamic. So let's let's backpedal on some of these assumptions. Now, whenever you get confused about the meaning of terms, it's always a good idea to look in the dictionary. So if you look up static and dynamic, for static, you get a lot of words about at rest, without motion, in equilibrium, showing little change. For dynamic, you see a lot of definitions that talk about, marked by change, marked by a productive activity, energetic, forceful, changing, etc. So we sort of have a general idea here that, the distinction between static and dynamic is changing versus unchanging. So let's run with that. And there's a couple of aspects here that we want to tease apart. One is, well, what is actually changing? And in the context when we talk about languages being static or dynamic, we tend to think of this strictly in terms of typing. Java is statically typed, Python is dynamically typed. But in fact, there are many, many other axes of static versus dynamic that languages and runtimes might engage in. So, for example, Java has, as I just talked about, dynamic typing. It also has dynamic class loading, dynamic class verification, dynamic class redefinition, dynamic compilation, which we call JIT compilation, dynamic recompilation, which we call de-optimization. This is where we may have JIT compiled a class, and then for whatever reason, the VM decides, I don't like that compilation. I want to throw it away and change it. So what happens is we evict the compiled code from the code cache, go back to the interpreter, and maybe recompile later. Call sites and field accesses in Java are dynamically linked. What that means is the first time client code calls a method in another class, there's a bunch of activity for, okay, what method are you actually calling? And this involves comparing strings for field and method descriptors. It only happens on the first call. Thereafter, the linkage information is cached, so it's not as slow as it sounds. But we do linkage dynamically, and that is what enables us to take a jar and drop a new jar onto the class path and have everything just work. Java has dynamic dispatch through virtual methods. It has dynamic introspection through reflection and features like instance of and casting. So, even though we'd like to think that Java is a mostly static language, Java is actually really dynamic. So one dimension of static versus dynamic is what is changing, what is not changing. The other dimension is when is it changing? Over what period is it changing or not changing? So earlier I described the sort of naive division of compile time versus runtime, which is usually the thing that comes to mind when we talk about something being done statically or something done dynamically. But in reality, there are many, many interesting, phase transitions in a program where something that happens, before a phase transition and is held constant, throughout the next phase is called static, even though it was dynamic in the previous phase. And as an example of that, take a line of code like this, where we say static final int seed equals, and then we go off to the hardware randomness source and we ask it for a random number. So is that static or dynamic? Well, duh, it says static right there, right? Well, so that's part of the story. But when does that initializer run, the get random number? That runs at runtime. That sounds pretty dynamic to me. On the other hand, the value of that seed is held constant for the entirety of its visible lifetime. So no one can ever see it change. Well, unchanging, that sounds kind of static. But on the other hand, this lifetime doesn't coincide with the sort of compile time versus runtime distinction. So it kind of gives you an idea that we're used to playing very fast and loose with these terms, and that can often get us in trouble. So one of the things that the JVM is very good at is optimizing things that were born dynamic as if they were static. So, for example, this static final field example, what the JVM is going to do is it is going to aggressively inline that as a constant into things like generated code and constant folding, constant propagation, and all of that, even though there's a real element of dynamism going on here. And this is really part of the JVM philosophy, that there is this yin and yang of static versus dynamic that is not a contradiction, it's a strength. And rather than choosing static versus dynamic, the Java answer is almost always both, please. And so, it's a core, we consider it a core JVM competency to optimize calculations that may look static for a certain period of time, even though they were dynamic in an earlier phase. And that includes things like the field initialization example that I just showed. And it also, includes things like class loading. Which is done dynamically and lazily, and lots of JIT optimizations take advantage of that. Another thing JVMs like to do and are very good at is hiding the evidence when it guesses wrong. So one of the coolest optimizations that JVMs do routinely is class hierarchy-based speculative optimization of polymorphic call sites. And what that means is, when you go to call a method that's defined, say, in an interface, ordinarily you would think, oh, that has to be a virtual call, and you have some idea of like what the mechanics of a virtual call is with, looking things up in vtables and things like that. But the JVM is entirely free to say, I happen to know that there's only one implementation of that interface loaded. So I know exactly where this call is going, and I'm not going to go through the vtable. I'm going to do a direct call. In fact, I'm going to inline through it. Right? And this is something that the VM does, but it's kind of a dodgy thing to do, because a minute later, I can load another class that violates that assumption and invalidates the optimization that I just described. Not a problem. It's the same JVM that's doing the class loading, that's doing the JITting. So when you go to load something that would violate a previous assumption, it says, wait a second, hold off on this class loading for a minute. Let me go evict some code from the code cache, because it has bad assumptions now. That will fall back to interpretation and get re-optimized later. And then I'll continue with the class loading. So this is an example of something that is dynamic, but if you squint, might be static for long enough that it's worth trying to optimize something, and if you're wrong, the VM is able to recover without exposing a failure. So this is something that VMs do all the time. We don't even notice it. It's a wonderful thing. This is why Java can often outperform C, because it's allowed to make optimizations that are not provably true, as long as we will know when they become invalidated. Similarly, we may want to de-optimize on the basis of we gathered profile information, compiled code in a certain way, then we gathered more profile information and decide, you know what, that was a bad compilation. I can imagine a better compilation. I'm going to kick that code out of the code cache and recompile it. So this is like business as usual in the JVM, is balancing this static and dynamic reasoning. Okay, so none of this has anything to do with startup, right? Well, let's talk about what happens at startup. So when a program starts up, like I said, there are activities that might be part of your program or your framework or libraries that you use, like reading configuration files or scanning for annotations, opening sockets, creating loggers, like I said, and also class loading, class verification, class file metadata construction, static initializers, interpretation, profile gathering, call site linkage. All of these things happen at startup. And similarly, at warm-up sort of extends over a longer period of time than startup. We see the same split of there are activities that are part of the program that govern warm-up, like populating caches, and there are JVM activities like JIT compilation, of hot code that affect warm-up. Okay, so $1 million question: why do we do it this way? At first, it sounds really inefficient to do what I just described, to do all of that work every time the program starts. Are you crazy? And the reason is dynamism benefits both the programming model and the performance model. So dynamic features like on-the-fly class loading and reflection make Java programs more expressive. The frameworks that we use every day would be much harder to write if we didn't have reflection, if we didn't have annotations, if we didn't have dynamic class loading. Similarly, dynamic compilation, JIT compilation, generally produces better code than static compilation for the very obvious reason that if you're compiling at runtime, you have more information than if you were compiling at build time. You have information about the hardware you're actually running on, not just the abstract Intel instruction set. You have information about that was gathered during profiling of what has the program actually done? Has this branch actually been taken? Has a null ever shown up at this dispatch site, etc.? And so we can use that information to produce better code. And then if it turns out that we gather more data and our opinions change about what would constitute a good optimization, we can de-optimize and re-optimize. And we can do that based on observed program behavior. So all of this dynamism makes for a good user programming model and excellent peak performance. So what's the cost? Everything's a trade-off. The cost of that is slower startup and warm-up. For some applications, think about like a WebLogic server, which starts up and runs for months, this is an excellent trade-off. The fact that it takes a while to start up may not be an issue, and the fact that you get better peak performance is definitely a good thing. On the other hand, if you have something like a command line application, the user is waiting to see feedback, they may care more about startup, and they probably don't care about peak performance because your short-running command line application probably doesn't even get out of the interpreter. So all of this is to say that different workloads have different requirements, and we want Java to be good for all of them. So to sort of visualize startup and warm-up, imagine there's an ideal behavior, which is given by this green line at the bottom here, where this is the amount of time it takes to do each task in a program that does repetitive tasks, which a lot of programs do. Some programs just do one thing and exit. And you could see that the timeline for the first task is going to be higher than for subsequent tasks because we do more work before the first task than we do before the second task. Now, most programs end up with something more like the yellow line, where you have the same qualitative shape, but the reality is that there's a big hit on startup. And then there is a gradual convergence between the observed performance and the ideal performance. So the work under this first unit of time is startup activity, and typically that's driven by things like class loading, class initialization, which are unique to the first iteration. And the stuff that is below the other line is generally online JIT activity, for identifying hot classes, compiling hot classes, and it's going to take a certain amount of time for the hot code to all be compiled, which is what warm-up basically means. So startup tends to be a very short-lived thing. Warm-up tends to be a longer-lived thing. So if we want to improve startup and warm-up, what do we have to do? Well, we have to find a way to push the first point down if we're looking to optimize startup, and to push the whole curve down if we're looking to optimize warm-up. Okay, so how do we push these curves down? Well, we need to move work off the critical path. That might mean moving it later in time, like being lazy about things, not creating loggers that we don't need to create immediately. Or we could shift work earlier in time, from runtime to build time or deploy time or packaging time, or some earlier phase of execution where we're going to run some Java code and remember the answer. And we can shift work, both of these categories of work that's part of the application, as well as shifting work on behalf of the application. And this is sort of old hat for what JVMs do. JVM already employs a lot of computation shifting techniques, such as garbage collection and constant folding and lazy class loading, etc. So a lot of these optimizations just fall out of the normal semantics of Java programs. So the if you have an arithmetic expression, x equals 2 plus 3, well, we could push a 2 and a 3 on the stack at runtime and add them, or we could do the computation at compile time. And the language specification allows us to do either, because it just tells us what answer we're supposed to get. It doesn't tell us how efficiently we're supposed to do it. So there are a lot of optimizations that we can do without, where the specification is agnostic on what we're doing. Similarly, garbage collection. The timing of garbage collection is not specified. Class loading is defined to be lazy, and class initialization is defined to be lazy. And so these things happen, these things just fall out of the natural semantics of class loading. There are other optimizations that involve work shifting that we might like to do that might require some work by the user to enable, or some specification changes to enable. So, for example, in the past we had an experimental AOT compiler which involves running a tool at build time saying compile those classes ahead of time. And similarly, we have the class data sharing mechanism, which involves caching information from a training run to accelerate startup. And shifting work is fair game as long as the program's meaning is preserved. So Leyden will, lean on what we're already doing with computation shifting by expanding the opportunities for computation shifting. So some kinds of shifting wouldn't require any spec changes at all. For example, like Lambda proxies are currently spun as at runtime the first time you evaluate a Lambda. That's something that could be moved to build time with no specification change. Similarly, speculatively compiling code ahead of time. When I say speculatively, that means code we'd be willing to throw away if something changed. There are other kinds of shifting that we might want to do that aren't allowed now, but we might extend the specification to allow it. So, for example, if you want to strip out code that that you know is not going to be run, or you promise is not going to be run, currently you're not allowed to do that because it could always be invoked reflectively. We would need to make some spec changes, which we may be willing to do, in order to support that kind of that kind of computation shifting. We may also, investigate adding things to the programming model that allow you to talk about constraints on the timing of computations. So, for example, maybe marking some static fields as lazy, which would mean you don't have to do this immediately, you can do it later if you want, or maybe you can do it earlier if you want. There's also an exploration going on called computed constants, which I'll talk about, which is a library-based programming model for shifting. So there's a lot of different options that we might want to pursue here. Now, some of the optimizations we might want to do might not be practical or safe without some additional permission from the user, in the form of constraints like, I promise this won't happen. I promise this class will never be redefined. And some programs may be willing to accept those constraints, and they may be willing to accept quite a lot of constraints if there is sufficient benefit. So one of the key values of Project Leyden is that we want users to be in charge of choosing which constraints they're willing to accept in order to get the benefits that they want. Because we know that different programs have different, different requirements and different goals and different, performance needs. If you look at the sort of extreme end of the spectrum, there's a somewhat severe constraint, which is the closed world assumption that the native image tool makes, and this basically says, I promise there isn't going to be any dynamic class loading. I promise that I'm not going to do any reflection except for the list of methods I give you. And if you're willing to accept that constraint, then we can shift a great deal more computation to from runtime to compile time. Not all applications are willing to live with such a constraint, and so what we want to do is explore a broader range of constraints that may start with no constraints at all, and maybe we can give you something with no constraints, and then we can give you a little bit more with some constraints, and then we can give you a lot more if you accept a lot of constraints. But the key is we want developers to be in charge of making these constraints and how they're going to, how willing they are to trade functionality for performance. So the sort of key concepts in this model are temporal shifting of computation, both forward and backwards, constraints on Java's dynamism as necessary to support the kinds of computation shifting that a user may say, I'd like to get this benefit, and I'm willing to consent to the requirements. We also want developers to be able to choose which optimizations they want and not, which constraints they're willing to accept and not, and this always has to preserve the meaning of the program. So these are the sort of ambitious goals of the project. So how are we going to achieve this? So a new concept that Leyden will introduce is a concept of a condenser. A condenser is a tool that runs at build time or package time or something like that, that takes a program image, performs some of the computation in that image, and creates a new program image that embodies the result of that computation. That might be new code, because we did some ahead of time compilation. That might be new data. It might be new metadata, like preloaded classes or pre-resolved call sites. It may be new constraints. The limitations on condensers is they have to be meaning preserving. They can't do arbitrary transformations of the semantics of the program. The resulting image has to have the same meaning under the selected set of constraints. We want condensation to be composable, that you can feed the output of one condenser into the input of another, potentially multiple times if you have to. And we want the users to be in charge of selecting how to condense and when. And like maybe if you're just doing testing or debugging, then you don't have to bother with any condensation. You can just run dynamically. And to the degree that shifting computation may require accepting constraints, the condenser configuration represents a certain set of trade-offs between functionality and performance. So we already do some of this in the JDK today. How many people here use AppCDS? How many people here know what AppCDS is? Okay, you guys are missing out on something here. So this is a feature that's been in the JDK for 2 decades. It started out as class data sharing, CDS, in the Java 5 timeframe. And it's basically a startup cache where it takes parsed class file bytes for common system classes like string and integer and such that get loaded in every invocation and caches them in a binary file that can be used to improve startup. And because every invocation is going to load string and integer and security manager and the same usual suspects, a few hundred classes, this was a significant performance improvement. But that's what CDS did 20 years ago. CDS has improved dramatically over time. So in Java 8, it was enhanced to cache Lambda proxy classes. In Java 10, there was added tooling so that you could say, hey, cache these classes too. Here are my application classes. I know we're going to get loaded at startup. Just put them in the AppCDS archive as well. And then when in Java 12, we added caching the module graph as well. So this is a mechanism that stood us really well, for a long period of time. That has allowed us to shift computation to build time to accelerate startup. And so if this has been working so well, let's double down on that and let's use that for caching other things that can improve startup, like profile data, like compiled code, like linkage resolution for method invocations. So the way AppCDS works is there's an archive file, which is a big file containing cached metadata. It gets memory mapped at runtime and is used to accelerate today class loading and tomorrow more things. The JDK has a default archive, which is built when the JDK is built. That happens on, before you download the JDK. So it's when we actually build the JDK image. And that will always get used unless you turn it off. You can turn it off. And it contains metadata just on JDK classes. But you can select, with a command line switch, a different archive file. And you can create your own archive files and specify which classes to preprocess, which includes both JDK classes and your application classes. Now, as the show of hands showed, most people aren't using this today, and they probably should, because you can get a reasonable startup improvement for a very, very small amount of work. It's not going to work miracles, but if it shaves 10, 20, 30% off startup, that may be enough for a lot of applications. So I'll give you a flavor for what these classes, what these configuration flags look like. They're not all that pretty. So like if you were going to use AppCDS today, you would perform one or more training runs, like running a unit test or something like that, with a flag that says, dump out the classes that were loaded. And it'll dump them out to a file. It's just a text file, so you can edit it and merge them and whatever you want to do. And then there's another set of flags where you can say, take this list of classes and create a AppCDS archive that caches the loading of those classes. And then you distribute that archive with your program, and your run script specifies that CDS archive when it goes to run your program, and your program gets faster. So to give you an example of the orders of magnitude that you might see with this, Java C compiling one file, not a bad startup test. With CDS explicitly disabled on somebody's laptop, we got 300 milliseconds. With the default CDS, we got 260 milliseconds. So, that's like a 15% improvement, not so bad. With AppCDS that did a training run that included the Java C classes that got loaded during compilation, we managed to knock 50% off the startup of the cold start alternative. And so, this doesn't necessarily get you everything you want, but it's something that you've been able to do for a long time, and it gets you quite a lot, for relatively little work. So it may be that, we take all of this and we turn it into a condenser as part of, the early work in Project Leyden. Almost all interesting techniques, for startup improvement rely at some level on training runs, which is to actually run some part of the program and observe what it did, observe what classes it loads, observe what methods are hot, which is basically allowing us to discover ahead of time what we would otherwise discover when we run the program dynamically. So you write a small driver program, which you might be able to reuse an integration test, and as part of your build, you run the training run, it dumps some data out, and then you do something with that data. It's a very effective technique for the same reason dynamic compilation is effective, because it allows us to base analysis and optimization on what did the program actually do, not just what does the program say. So as a kind of experiment in the last few months, we've been trying to identify what can we do about startup at the least constraining end of the spectrum. Let's assume we're not willing to impose any new constraints, not change the spec, not sacrifice any dynamism, not give up on running any Java code. How far can we get? So I have some experimental numbers that I'll show you. But first, I want to talk a little bit about how dynamic compilation actually works. So in the hotspot JVM, there are a number of tiers used for compilation. Tier 0 is the interpreter. We have two compilers. There's C1 is a fast compiler that produces OK code. And then C2, or the Graal-JIT, are highly optimizing compilers that produce awesome code, but they take longer to run. So tier 0 is interpretation. Tiers 1 through 3 are various configurations of the C1 compiler. And tier 4 is using the highly optimizing C2 or Graal-JITs that benefit from profiling information gathered by running in the interpreter or running C1 compiled code, but in general don't collect nearly as much profile information. So startup mostly happens in tiers 0 through 3. So we start with the interpreter, and then we graduate to C1, and then eventually we figure out what code is hot, and we compile it with C2 or Graal. And during that time, a lot of things like symbolic resolution, symbolic linkage, class initializers get run. This all happens in the interpreter or in C1 usually. Warm-up happens as the code we're running shifts from the lower tiers to the higher tiers. We use the lower tiers to gather profiling information. The JIT then uses that to make better optimizing decisions. And the reason that we do this in a tiered fashion is if we gather profiling information early, we can make better compilation decisions when we run the more expensive compiler. And peak performance is reached when all the hot code stabilizes in tier 4. JIT compilation is what we call speculative, which means the machine code that we generate, we're always free to throw away. And then we just bounce back to a lower tier. We go back to the interpreter. We go back to C1. And there are many reasons why we might de-optimize and go back to a lower tier. Maybe there was an environmental change, like a new class got loaded that violated one of our assumptions. Maybe profiling data told us the code that we compiled before is no longer optimal. Maybe we ran out of space in the code cache and had to make more room. Maybe the user is using the debugger, and that caused some code to de-optimize. So JIT compilation it's pure optimization. It's one that we can freely do or undo. So since we said, what can we do that doesn't involve any changes to the programming model or to the code, we want to lean as heavily as we can on existing components in the VM, like CDS and like our JITs. And so what we do is basically taught CDS to gather additional information that is discovered during a training run, like invocation profiles, like JIT compiled code, like class mirrors, like foo.class. Resolved constant pool entries, resolved linkage states, pre-initialization of some of the simplest classes. And then when we go to load a class, or we go to, we can look in the CDS archive and say, do we already have the metadata for this? Great, we'll just reuse that. Do I have JITted code for it? Fantastic, I'll just use that. And so this is basically another big computation shifting trick, where we cache profiles and compiled code and linkage states from the training run, and we reuse them in later runs. And there's a lot of different ways to slice and dice this. We could use this information not to cache JITted code, but to do better scheduling of compilation. Or we could load JITted code from the archive. There's also tricks that we can do about do we delay loading the code until all its preconditions are met, like all the classes on which it depends is initialized. There's a lot of tricks that we can do with existing concepts in the runtime. The cool thing about this is all of this is still speculative. And so a cache profile or cached code is a record of a dynamic observation of an application from a previous run. So we can use this information the same way, maybe with a little bit less confidence, as we do for profile information gathered in the current run. And if it turns out this doesn't work, if one of our assumptions is violated, we still have the option to de-optimize, reprofile, re-optimize, etc. And so this is an approach that deals really well with surprises at runtime. Because things do change between training time and production, and we don't want the application to fall over and break. We're more willing to say, all right, well, it just won't start up as fast if you change something. And this shouldn't be surprising, because this is stuff that Java has been good at for decades, right? On-the-fly adaptation is one of Java's biggest strengths. So there were 100 reasons why we might de-optimize. Something changed since training run is just one more of those reasons. So some numbers. So we have the same ideal green curve, which is made up, and we have the yellow curve, which is an observation of really running a program without any of these tricks. And then we're going to add in this red curve, which is an observation of running the program with all these tricks that I just described. And so for compiling Java-C, running Java-C to compile 100 class files, we're able to see roughly 2x startup improvement and a pretty reasonable warm-up improvement. We were able to bring down both the startup number and bring the yellow line down closer to the green line for not very much work. We didn't have to change any code. We didn't have to give up any dynamism. We just had to do a little bit more work at build time. So that's a pretty decent payoff for not very much work. And the numbers there represent not just one trick, but a lot of different tricks that work together to give us a reasonable startup improvement for not that much work. It's still early days. One of the things we spend a lot of time on is tuning VM policies like compilation policies, and this is more of the same. And so these are just pretty much rough numbers from the lab. Here's a kind of interesting one where we did the same thing with an XML validation benchmark from SpecJVM. And we didn't see any warm-up improvement, but we did see like an 8x startup improvement, which what this tells us is different workloads have different behaviors. It's probably the case that there was a relatively small amount of code involved, involved in this workload that was identified to be hot relatively early. But there was a lot of work, setup work, that we were able to shift at the beginning. And sometimes like startup is the only interesting win, and that's fine, and we can take that. All right, so the last example I want to give, and then we will wrap up, is Spring Boot Pet Clinic, which is sort of typical Hello World ++ Spring application. And there's a few data points here. The first bar is startup time with just ordinary JDK 22, no tricks. The yellow bar involves unpacking the application, which eliminates a lot of activity of loading classes out of jars, which is something that people do all the time when they deploy these applications anyway. The next two bars, the light and dark blue, are various combinations of applying the improved CDS that I just described, of caching different things in the CDS archive. And the last bar brings in the Spring AOT tools, which is basically like a condenser that is Spring specific, which basically does a training run, observes all of the annotation scanning and wiring of beans and all of that, and caches that in a faster to start up way. And all of these different techniques synergize so that running more of these techniques gives you a better result. And so what we saw was a roughly 4x startup improvement. Again, not giving up anything, not giving up any dynamism, not changing any code. So there were a lot of things that fed into these numbers, and there are more things that we're going to do in the future. Like I said, we're sort of just getting started here, but a lot of these tactics are additive, and so doing more of them together can give you a cumulatively better improvement. So early class loading is a win. Caching compiled code is a win. These are not surprising. Resolving invoked dynamic call sites is a smaller win, but still worthwhile one. The framework-specific analysis that Spring does is really valuable, because a big part of what applications, like Spring applications, do at startup is annotation scanning. And that involves a lot of relatively slow paths, and that can be observed through a training run and recorded. But the upshot of this is that time-shifting speculative optimization works pretty well. It's a promising approach that gives us significant, although not as much of a gain as you would see with something like native image, but not with all the constraints that native image requires you to accept. So you can get with the giving up nothing end of the spectrum, you can get some decent gains without giving up, any compatibility or dynamism, or changing your code. And so what we've kind of done here is, like, you can think of like this work and native image as a pair of bookends, right? So at one end of the spectrum, we're saying, how much can I get giving up nothing? At the other end of the spectrum, we're saying, how much can I get giving up a lot? And then there's a whole spectrum in the middle of, okay, can I give up some of those things and get some of the difference? And we will continue to drill into the space in the middle as we move forward in this work. So I just want to talk briefly about another exploration that's going on in Project Leyden, which is a programming model, library-based programming model exploration called computed constants. And this is about shifting computation later in time. It's a mechanism for greater laziness without giving up the optimizations that you get from static final fields. And so, the JVM already contains a known optimization for optimizing mutable static fields as if they were final static fields, if it knows that it will eventually converge to a stable value. And it's a sort of a dodgy kind of thing, and so it has not been made available as a general purpose optimization, but it's something that you see in the JDK code. You see some code annotated with the internal annotation at stable, and this is a hint to the JVM that says, once this is initialized, treat it as if it were final. And this is a really good example of that kind of static dynamic yin-yang. It's a fully dynamic computation, but the VM is able to say, oh, well, if I look at it through this lens, I can treat it as static. And if I see somebody assign to it, well, I know the assumption is violated and I can de-optimize. So this is a cool optimization that we do internally, but it was not ready for broad consumption, which is why it's internal only. So the computed constants exploration, which is still in the early phase, it's a draft JEP for it, it exposes that same optimization to user code. And the way it works is you declare a computed constant, and you give it a lambda to initialize it. And the first time anybody goes to read that computed constant, it goes and runs the initializer, and thereafter caches it using @stable so that you get basically the full performance of static final fields with the laziness of what looks like a dumb library for lazy initialization. It's not as dumb as it looks. But what this lets us do is to say, identify individual calculations that say, this calculation doesn't need to be done so early, so I'm going to mark that as lazy, let it be shifted until it's needed, without giving up any of the optimization benefits that we would ordinarily get from static final fields. And this mechanism may eventually be extended to talk about shifting earlier in time to earlier phases of computation, but we're still early in the process of that. So there's a lot of work left to do. We have a prototype of condensers and a condenser toolkit. We have a lot more investigation about what other forms of computation can we shift and what are the most interesting middle ground constraints that might allow us to do more shifting. And I think the biggest challenge is finding the right way to bring shiftability into the programming model so that the user is able to say, here's a computation that has certain semantic properties that the JVM can then identify as, oh, under these conditions, I know I can shift that. So we're just getting started. There's a lot left to do, and I see my time is just about up, but I think we have time for a few questions. So, all right, any questions? So the question is, what can you use in production today? So all the work that I've described so far is highly experimental. And so if you want to use experimental code in production, well, you can do whatever you want, but it's not in a JDK anywhere yet. What I expect you will start to see over the next couple of releases is some JEPs that describe smaller pieces like improvements to CDS. But what you can use in production today is app CDS. and that is has been, like I said, it's been in the JDK for years and years. It has tooling for dumping and customizing CDS archives. So that's not everything that I just described, but you can use that today. You can also use native image today if your application is suitable for the constraints of native image. And I see you shaking your head, so so we understand not every workload is willing to accept those constraints. More questions? I can't see anything, so there's a hand over here. Okay, I'm sorry. Yeah, that's a great question. So the question is, let's say I opt into a constraint at build time, and then that constraint turns out to be violated. What happens? So I think it depends. So with for example, with @stable, you're making a sort of promise to the VM that says this thing won't change after its value stabilizes, but the JVM doesn't believe you. So the optimization it does is speculative, and if it sees you do a put field or a put static to that field, it will say, oh, wait a second, now I have to go invalidate a whole bunch of code, which might be an expensive revocation. So the consequence might be an expensive revocation, or the consequence might be an exception. If you've said, like, I promise I'm not going to redefine this class ever, and then someone tries to redefine that class, maybe you'll get an exception that says, redefinition is denied because this condenser configuration marked this class as non-redefinable. So I think it depends on whether there's a recovery possible or whether we just have to say, you lied to me, goodbye. All right, I see a question right under the very bright lights over there.
So on the previous slide, you showed the example of
Why was the field not static? Oh, well, not final. Yes, because PowerPoint is a terrible IDE. So we're going to fix that right now. Okay, public static final. Okay, what were you talking about? Yeah. So thank you, Mr. Compiler. Any other questions? Yes, question in the middle there. And I think that's probably the last question we have time for. So the question is, how is this related to Crack? So they're related in the sense that they're exploring the same goal. So Project Crack basically says, let's assume a checkpoint mechanism that's outside of the JDK, whether it be CREU or some cloud-based checkpoint mechanism. Let's run the application up to a certain point, freeze dry it, and then restore it. And then, well, that may not work because you may have done things like open sockets. So you have to register handlers for things that have to be redone at restore time. So I think Crack is an interesting exploration. I'm not particularly optimistic about it because it is not something that allows you to validate that your program is correct through any sort of sensible analysis. You sort of have to debug your way into correctness by trying things and seeing what fails. The problem with Crack is that it's trying to interpret old code with new semantics and hope everything is good. And if it is good, great. It gives you great performance numbers. If not, you just have broken code. And maybe if you're lucky, you get an exception. But maybe if you're unlucky, you just get wrong answers. And those wrong answers come from assumptions that are violated deep in libraries that you didn't even know were part of your application. So I think Crack is it's a good exploration. I think it's but I'm not optimistic about it as a programming model. I would much rather give people a programming model where if they, whatever code that they have will run correctly 100% of the time, and then if they do some more work, they can make it run faster. Crack tries to make things run faster, potentially at the expense of correctness, and I don't like that trade-off. But I think it's an interesting exploration. I'm glad it's going on, but I wouldn't bet on that direction. All right. Thank you very much, everyone.